All right, welcome back. In this second half, we're going to talk about processing that digital signal that we learned how to digitize in the first half. And you notice we're now processing our measurement here. So let's see how this works. So as far as agenda goes, we're going to talk about some DSP fundamentals, really go over the basic stuff you need to know. We'll talk about two functions, spectrum and autopower, and why we might want to pick one versus the other. And we'll talk about something called leakage and something called windows to wrap up our agenda. Sound good, Pete?
That sounds awesome.
Great. So fundamentals. As Pete mentioned, ultimately we're acquiring the signal and we want to analyze that signal to help solve a problem, right? And we're using computers to do that. And so that brings with it some challenges, right? So we're doing digital signal processing, and we have to remember that computers are not analog devices, they're digital, and so they're switching things on and off, hopefully very intelligently, but ultimately we're going to end up discretizing in time, like we looked at before, as well as amplitude, and this results in a big loss of information, right? We're only looking at the signal every so often and writing down the amplitude with only so many options for amplitude, right?
A massive loss.
Massive loss.
Okay.
Yes. One of the things we're going to use to our advantage is we're going to bring that analyzed or that digitized signal into some different domains, and each of these domains will have a little bit different area of expertise, if you will. So time, frequency, and the Laplace domain are three big ones. So if we look at these three different domains and how we move from one to the other, you can think of these different domains as a coordinate system where certain aspects of the signal are going to be highlighted. Okay, so two of the biggest ones we're going to use today are time and frequency domain. And each of these domains has a specialty of pulling out certain aspects of the signal and helping us analyze them. Time domain, this is where we have things like a differential equation of motion, right? We want to know where the mass positions are going to be in our spring mass system as a function of time. Frequency domain splits everything up into the periodic components, right? And that's why we're always talking about sinusoids and cosines and things like that. If you do any modal analysis, you're transitioning into the Laplace domain, which describes everything as these poles and zeros. How do we move back and forth? Well, between time and frequency, that's where we're going to spend our time today, and it's this transformation back and forth. And the nice thing about it is that we can move back and forth and we're not throwing anything away. There's no information lost, okay? So how do we do this? Well, if you've ever heard the term FFT or Fourier transform, it's all based on the work of this guy, Joseph Fourier. And in the 1800s, he did some research on heat transfer and came up with this analytical theory of heat. I won't try to do the French pronunciation. It's been quite some time since I had French in high school. And it analyzed heat conduction in terms of these infinite mathematical series. The nice sort of byproduct for our use today is that the end result of this is that you can take any system or any function rather and describe it uniquely with a set of sine waves of certain magnitudes, frequencies, and phases, okay? And sort of illustrating that is this picture here. You see different size circles being drawn. The phase angles are all a little bit different. If we add all of those together, we get the function of the drawing of the hand. Okay, so that drawing of the hand is a function, and we can describe it perfectly using a Fourier series or a set of sine waves, and that description is unique and perfect. Okay,
that's
and we can move
blowing my mind. Thanks for that.
Absolutely, that's what I'm here for, Pete. So Fourier said, here's a weird time signal. I can describe that perfectly. So we input into our FFT any time domain signal. Okay, so a bunch of squiggly lines in the time domain looks complicated. I don't know what the heck that is. Fourier, no problem. He says, let me see that. Oh, that's just the sum of these sine waves, and I'm going to help you split them apart. And so the Fourier transfer takes that input in the time domain and splits those components out and plots them in the frequency domain. So the output of the FFT is this frequency spectrum here. Okay, this sine wave at this frequency at this amplitude plus this one equals this original signal.
So you kind
Okay.
of broke it down into some different parts. But it's the same information, frequency and time?
Yes. Yep. Just
Okay.
looking at it two different ways in two different domains. That's exactly right.
All right.
To help us along our way, we're going to review some basics of sine waves because we're going to break these time domain signals into a family of sine waves, if you will. Just review some things. The period of a sine wave we'll call this capital letter T, and that's the amount of time it takes for the sine wave to go through one cycle, okay, and start to repeat itself. The inverse of that time is what we call the frequency, or 1 over the period, and we say how many cycles per second, and we give that a new unit called the hertz, okay? And so this sine wave has some frequency and period to it and some amplitude, denoted by this circle's radius here. If we translate that to frequency domain, we get a certain amplitude, which this amplitude here is the same as the radius of this circle, and we just show that amplitude at a particular frequency, okay?
All right.
So if I said, here, Pete, I've got a sine wave, and here's all the information you need, what is the frequency of this sine wave?
Well, you got 2 complete cycles of that sine wave over 1 second. So I would go with 2 cycles per second or 2 hertz.
Very good. Very, very good.
Wow, he survived.
See, in the first half, I had to play the dumb guy, and now the second half, Pete has to play the dumb guy.
I survived the first round.
That's right. All right, I'm going to throw a curveball at you here. Now I've changed that sine wave. What have I done to the sine wave, Pete, moving from left to right?
I think you've got more cycles over the same amount of time. So I'm going to go with you've increased the frequency, like doubled it, because I see double the number of cycles.
That's exactly right. Nice work. So double frequency. How about now?
Ugh. Well, I don't know about your drawing, but I suspect you have the same frequency, but you've doubled the amplitude, perhaps? Although I don't know if that's exactly 10 volts there.
If you don't trust my PowerPoint art skills by now, Pete, man,
I don't know. I'm going to get a measuring tape out.
Go for it.
All right.
Go for it. Yeah, double amplitude, right? Frequency is the same, but we've increased the amplitude. Okay, here's another question for you. What is the amplitude of this sine wave?
It's 5 volts, right?
That's one way of saying it, right? I could say 5 volts peak. Is there any other way to describe this amplitude?
There should only be one way, otherwise it'd be...
Well, it's confusing then, because there are at least 3 ways.
I guess if you went from -5 up to +5, what would that be? 5 volts peak to peak or something?
Well, it shouldn't be 5 volts peak and 5 volts peak to peak, right? It would be 10 volts peak to peak, or twice the peak amplitude.
Yeah, that's what I meant. I wasn't confused at all.
Good. Good.
2
Just
times the
everyone
peak.
listening.
Peak to
That's
peak
right.
is double the peak.
That's exactly right. Is there any other way you can think of?
I bet some key mathematicians came up with something like RMS.
That's right. Electrical guys like to talk about the RMS, or root mean squared amplitude, which is the peak value divided by the square root of 2. Okay, so that would give us 3.5 volts RMS. Now, all of these are perfectly correct. They're all the right amplitude. It's just a different scaling, or a different unit, if you will. The units are all volts, but it's just how we scale the amplitude. Okay, so you need to be aware of when you're looking at a frequency spectrum, is it peak, is it RMS, is it peak to peak? Because the values can change quite significantly.
Yeah, you better know in the meeting you're in. I know sound guys also like RMS, like it's dBs, but it's actually dBs RMS.
That's right.
Vibration guys like peak, so.
I don't like to put people in boxes, but you're probably pretty accurate. Okay, so we also talked about the output of this Fourier spectrum, or the Fourier transfer, being a spectrum. So what does that mean? Well, it's actually a series of complex numbers, okay? And back to your mathematics days, a complex number has 2 components, this a plus ib, or jb, depending on where you went to school. And it just means that we have a component in what we call the real axis and a component in the imaginary axis, denoted by this I here. this is the actual value, and we can describe this value, the position of this dot, either as a component in the A plus a component along the imaginary axis. And we would call this the real and imaginary form. Or we could say it is a certain magnitude C at some angle from the real axis theta. Okay, so real and imaginary, or magnitude and phase, are the two ways that we can describe these spectrums. Okay, and we have one of these complex numbers for every single frequency line in our frequency spectrum. Okay, so we have one at every single frequency line, and it has both of these components. Okay, let's take a quick look at a demo real quick at these two different formats. And so let me jump to this other project. So I've got a sine wave here, and let me start here. So this is kind of a more classic view of our sine wave, right? It starts at 0, goes up, and then it's just repeating over and over. This bottom half of my plot is what we call a Bode plot, and I believe it's the second shortcut in your test lab shortcut menu here. And Bode plots just mean it's a combination of both the real and the imaginary portion, or I can also plot that as amplitude and phase. Okay, so if I take the frequency spectrum, this is a 1 hertz sine wave, so there's 10 cycles here in 10 seconds. And so if I take this spectrum and I drop it in my Bode plot, you see I get a real component and an imaginary component. Okay, and I can do the same thing for magnitude and phase. I drop that same spectrum into the other plot, and I get a different plot in my Bode plot, right? This one's real and imaginary, so if I put a cursor here and I specify it as being at 1 hertz, I can see it's 0 degrees phase, so I have 0 in the imaginary, so it's essentially just all of its magnitude is along the real component. See, my amplitude up here is 1 Pascal, so this is a Pascal trace, and I see my amplitude is all in the real, so it's right along that real axis. There's no y or imaginary component, so I have 0 in the imaginary, all of my amplitude in the real. Okay, let's look at the magnitude and phase, do that same thing here, and I will see exactly the same information. All of my magnitude is 1, and it's at an angle of essentially 0. Okay, so right along that real axis. Now, let me show you this sine wave here. What have I done to this sine wave here, Pete?
It ain't starting at 0 no more there.
That's right. I have shifted it by 45 degrees in terms of that unit circle.
It's kind of
so
like
now
doing
it's-
a measurement, and if you start at a certain spot, you might start at 0, or you on the same sine wave, you could start at a different spot when you start the measurement, huh?
That's exactly right. Yep.
Hmm.
Depending on when I hit the start button, I might get both measurements could be perfectly correct. So I dropped that spectrum in here and my magnitude and phase version. So if I go to real and imaginary, so now 45 degrees on that unit circle, I have,
Some real, some imaginary now, huh?
yeah, and they're exactly the same, right? Because I'm at 45 degrees, so I've just got 0.707 in my real and 0.707 in my imaginary. If I look at the magnitude and phase version, put this guy right at 1 hertz. Here I've got magnitude of 1, phase angle of 45 degrees. Okay?
All
So
right.
the information's exactly the same, whether I want to see it as a magnitude and a phase or a real and imaginary, it's totally up to me. But because I've computed a spectrum in test lab, I get both of these components of the complex number. Okay?
All right.
So that's a Bode plot. And so when we move from the time domain to the frequency domain, there are some characteristics that we like to highlight. And we've already talked about the sine wave, where we have a sine wave here and we get a single frequency component at a certain amplitude, right?
Right.
Well, if you think back to our filter example, I said there aren't a lot of square edges in nature. And so here we have a square wave where essentially we go from minimum to a maximum instantaneously or as close as possible. What do you think this generates in the frequency domain, Pete?
Set of harmonics that are odd integer multiples.
That's right. So you see it's not just a single line here, but I've got 4 shown here. And I do not have the frequencies shown here, but you're right. This would be 1/3, 1/5, 1/7, 1/9. And these 3 dots indicate that that goes on technically forever. So I have an infinite set of sine waves in order to produce a truly square wave in the time domain. Okay, so things that are sharp or short in the time domain are very broad or have infinite amount of frequency content in the frequency domain. That's going to keep coming up as we talk more and more today. So if I have a damped sine wave, so I release this spring mass system and it dies out, our frequency domain is no longer just a single component, but it's really a bunch of components with a peak value at this sinusoidal frequency. Okay.
Yeah, so that's what it had to do to describe this signal. It's kind of a bit different than the sine wave, which was a single frequency.
Yep.
Still a dominant frequency, but I guess that smearing out is how it damps it out, huh?
Yeah. So this is a unique signal. A and C are unique. So A and C's frequency domains have to be unique because they are a one-to-one relationship, frequency to time. And if we had a true impulse function where it has 0 width in the time domain, I would get a perfectly even or flat frequency spectrum of infinite number of frequencies. Okay. So we use this principle in impact testing for structural dynamics all the time, where we impact the structure with a hammer. We're trying to put a little impulse in there, and we're trying to, excite a family of frequencies in the frequency domain, and that's why we use an impact as opposed to something else. Okay.
So when I make the sound ding, there's broad frequency content.
Sure. We'll have to record it and do a frequency analysis, but yeah, there's more than if you were to whistle or sing a note.
The whistle would be
Do
like
not
this
be here. No.
sine wave.
Yeah, but please don't do that. We don't need to hear it. Okay, so the point is we sample in the time domain. We use this FFT, or the Fourier transform, to move into the frequency domain. There's also an inverse frequency or a Fourier transform, and so we can move back and forth between the time domain and the frequency domain, okay, by transforming back and forth. And this orange box is just to show you we don't lose any information moving from one to the other. It's not like sampling, going from analog to digital, where we lose information. This is a perfect transformation. Okay?
Yeah.
So here are some factors you're going to want to familiarize yourself with. In the time domain, we're going to make some decisions about how much data we're going to take, how fast we're going to sample, block size, all that sort of thing. And each of these decisions is going to have implications in the frequency domain. So just memorize this chart and good luck. Well,
right.
This looks a little intimidating, so we're going to help you break this down, okay? And so we're going to sample in the time domain, and so we're going to set probably a sampling frequency, and that's going to dictate this delta t, the time between samples. But the way I like to tell people to approach this quandary is to ask yourself, what is the maximum frequency I am interested in measuring? Or what is the bandwidth in the frequency domain that I need to capture and analyze? So if I'm working on a noise issue, I'm going to want to capture the human hearing domain, which we'll talk about later this week, but that's 20 kilohertz. Okay, or later today, depending on when you're watching this. But so 20,000 hertz would be my maximum frequency of interest. If I'm working on a structural problem, maybe I'm only interested up to 100 hertz. Okay, but I need to decide how far up in the frequency domain do I need to look. And once I know that 100 hertz number, that's going to set some other things for me. Okay, based on this Shannon sampling theorem, I take this Fmax, or the maximum frequency of interest, and I need to at least double it. And that will be my sampling frequency, okay? And this is to help us understand the data that we're going to get out is not going to be aliased, okay? It's going to help us solve this aliasing problem that we talked about in the first half. So our Fmax is going to be our sample frequency divided by 2. That sample frequency is going to set this delta t, how much time the analyzer is going to wait between taking these samples in the time domain. Okay. So if we look in the frequency domain, we set our sample frequency, and we know we're only going to be able to look up to half that, because our Fmax is sample frequency divided by 2. And this will end up being our usable frequency range, or what we call our bandwidth for our measurement. Okay. Now, realistically, we're also acquiring or digitizing all of this data, but we know we have to throw it away because there's no useful data out here, and that's because of this aliasing problem that we talked about in the last section. Okay. And so we sample at least twice as high as the frequency we're interested in, only because we need to get around this aliasing problem. And we have an anti-aliasing filter which helps us as well. Now on the signal acquisition part, we get these bandwidth selections right in Test Lab, and so now we know what this bandwidth means. We have this resolution, which I see as a Hertz value, and then we have this frequency line. So once I get past this bandwidth, I start losing an idea of what I'm doing here. So let's talk a little bit about these other decisions we need to make in the software. So we talked about this time domain sampling ends up in a frequency domain spectrum. This delta F, or how many spectral lines we have, or how many hertz between all of our spectral lines, this is our frequency resolution. Okay, and we can see down here, this is 1 over this capital T. And what is this capital T? It is this full measurement. Okay, so our full measurement for 1 FFT is what we call capital T, or observation time. And that T, how much data we take, dictates our frequency resolution on the other side. Okay, so it has nothing to do with...
That's the time we're going to use to perform a single FFT. So if I have a 30-second recording, my time could be 1 second, because I might do 30 separate FFTs.
Yeah, we're going to get to that in just a second.
Okay.
But depending on if I have 30 seconds of data, I could choose anything up to 30 for my capital T, or down to 1 second or half a second. That's right. And so the choice will come out later. But this frequency resolution only has to do with that capital T that I use for my measurement observation. And so this relationship right here, that T that I use, dictates my frequency resolution. It has nothing to do with sampling frequency, which is sort of the natural inclination. If I want finer resolution, I want 1 hertz resolution, I must have to sample faster than I do if I want 10 hertz resolution, and that is not the case. Okay, it has only to do with how much time data I use for that FFT calculation.
That's kind of amazing.
Yeah. So we sort of break down this acquisition setup process like this. Determine your highest frequency of interest. That sets your sample rate. Forget about sample rate for the minute, because now we're just going to talk about the FFT itself and what we want for frequency resolution. We have to think about frequency resolution, and that's going to dictate that capital T, or how long I use for each FFT. So in Pete's 30-second measurement, I might choose 30 seconds, and that would give me 1/30th of a hertz resolution. It would be very, very fine, right? I'm going to throw onto that, or add onto that, step 3, which is decide whether we want tracked processing or stationary processing. And that sort of speaks to the question Pete asked about, do I want 31-second measurements or FFTs, or do I want 1 30-second FFT from my data? Okay. But ultimately, the thing we need to write home about is the shorter the FFT observation time, this capital T, the coarser my delta F is. And the inverse will also be true. If I use a bunch of time or a long delta or long T here, I'll get a very fine delta F. Okay. So in acquisition or online processing, we have these bandwidth, resolution, and frequency lines. I'm going to set my bandwidth and my resolution. Frequency lines will take care of itself. Post-processing, we have the additional option to set this frame size, and this speaks to Pete's question. Okay, so post-processing, we've got this 30 seconds of data. Do I want to use all of it, or use a smaller portion for each individual average? Okay, so if you think about it, this slide is showing Pete's full 30 seconds. I could take a shorter version of that. Let's say this is, if the whole thing is 30 seconds, let's say this is 5 seconds here. So frame 1, I use 5 seconds of my data. Then the second frame, I use the next 5 seconds. Frame 3 and frame 4, turns out Pete's only got 20 seconds of data here because 4 frames of 5 seconds each, but neither here nor there. Each of these frames is going to result in an FFT spectrum. Okay.
I'm glad it was 20 seconds because it's hard to divide 30 by 4 in my head.
Yes, yes, me too. That's why I changed it. So if I want to, I could have 4 frames of 5 seconds and end up with my analysis resulting in 4 different FFTs or frequency spectrums. Okay, and I have to choose whether I want to keep those separate or combine them through something called averaging. Okay, and so that's where I make this decision. Do I want to do a tracked measurement or a stationary measurement? What does this look like? Well, if I keep the 4 frame FFTs separate, I can keep them separated either by time or maybe RPM or position or whatever I want. And I can see how my frequency spectrum changes versus that tracking parameter, let's say versus time. We see the frequency content of our first frame is a lot different than our 4th frame in this instance,
Yeah, the
right?
vibration's getting bigger over time in this case, I guess.
Yeah, and maybe that's important for me to know. Or maybe I don't really care. I just want to get an average answer. I can combine and average these 4 FFTs and result with what we call an averaged frequency spectrum. Okay.
Yeah, if the signal was very constant, yeah, I guess stationary would be very appropriate.
Yeah. On average, for 30 seconds, this is the frequency content of our phenomenon, right? Right. But if it's changing this much, I think I'm going to want to stick with the tracked because I can always get to stationary after the fact, but that's neither here nor there.
Yeah.
Okay, so those are some of the choices we need to make. So spectrum versus something called auto power. Let's talk about this a little bit. So when we take some time data and we want to calculate some of these spectral functions, we already talked about the spectrum a little bit. We're also going to talk about 3 different variants of the spectrum, which we'll call auto power, and auto power PSD, and then auto power energy spectral density, or ESD. Okay, this is what they look like in test lab when we calculate them. Let's take a look at each of these. We already talked about the spectrum. It is a complex value, so it's going to have magnitude and phase, or real and imaginary components. The nice thing about the spectrum is that if we look at the frequency spectrum and it has a mean, so if this was a DC coupled signal and there was some mean in our signal, like this sine wave goes from 0 to 2, the mean of this signal is actually 1, right? It's a 1 hertz sine wave, or yeah, it's a 1 amplitude sine wave, but it's offset. And so we look at the 0 hertz component and it tells us that it's offset, right? So the 0 hertz value is the mean of the signal. The big thing about spectrum is we have to be careful with how we average these things, okay? And so over time, if I just calculate spectrum after spectrum and average them all together, and I have some random noise in there, I'm going to end up with 0 for my answer, and we'll see why that is.
But 0's good if you're trying to reduce vibration, right?
Yeah, but if you're fooling yourself and getting 0, it's bad. So get linear units, and there are certainly specific applications where we want to use it. Okay, so we talked about this A plus IB for the spectrum. We have only one format, and that is linear. We can have the amplitude as peak to peak, or RMS, like we already talked about. And these are sort of the amplitude math conversions to move from one amplitude mode to the other. Okay, so that's spectrum. Most commonly used, I would say, is this guy called the auto power. Okay, and it's the spectrum multiplied by the spectrum's complex conjugate, and we'll talk about what that means. The nice thing is we don't have to worry about how we're averaging. We don't have to be so careful because we will always obtain an amplitude average when we average auto powers. Okay. To complicate matters, we can have a little bit different format here. We can have linear or we can have power format, and so this kind of confuses people sometimes. But we'll show why you would do one or the other and how you get from one to the other. And when do I use an auto power? Well, it's when I really just care about the frequency content in the signal. I don't really care if these two parts are going up and down together or if they're going up and down out of phase. All I care about is how much of these two things going up and down. Okay, and that's 90% of the time all we really care about in generic noise and vibration problems.
In other words, if I don't care about phase, I can use an auto power.
Exactly. Yep.
Okay.
So if we look at this auto power and we see it's the spectrum times its complex conjugate, all that means is that we take this A plus IB component and we multiply it by the negative imaginary counterpart. Okay, so now we do this mathematics through and we do the multiplication. We see these center terms cancel out. Got this negative I squared. I is the square root of -1, and so we end up with A squared plus B squared is what this guy is. And we learn from our friend Pythagoras, A squared plus B squared is C squared, or the magnitude squared, okay? So it's this C term squared, and so that's how we end up with these squared units. It's because we're taking two pascals or G's or whatever, and we're multiplying it by another pascals or G's term, and so we end up with G squared. Okay.
So when you use auto power, you have G squared or Pascal squared as your units?
That's right. But before I lose you, Pete, on the squared units, I know it's a little bit confusing. The nice thing is I don't have to worry about this averaging anymore. So if you think about a spectrum, right, we talked about this when we were looking at the sine waves. Acquisition 1, I get this nice sine wave that starts at 0, but acquisition 2, I start at a slightly different time, and he happens to be the exact opposite in phase. And so if I add these two together, I will end up averaging to 0, right? And so I don't want this. I took two measurements with some amplitude. I don't want to end up with 0. When I do an auto power, remember I'm squaring everything. So even these negative amplitudes, a negative number squared gives me a positive number. And so I end up with a fully positive valued function. And so now I can add these two together, divide by 2, and I get a perfect average of my signal. And I don't have to worry about phase anymore because there is no negative phase.
So if that sine wave on the left was going from 5 G's to negative 5 G's, 5G squared is 25G squared, negative 5 G's is squared is 25 G's. So that's how it kind of ends up coming out. Not to be 0 because we squared it.
That's right. Yep.
Okay.
And so when we're talking about amplitude or auto powers, we can sort of use this power format, which would be the amplitude squared, so G squared or Pascal squared or whatever. In our peak format, there's also peak to peak in power and RMS in power. Or we can just get back to the linear format by just saying, okay, I'd have this power calculation, but if I just took the square root of that, I'll end up back at A, and that would be a linear peak auto power. Okay, so that's why we have auto power linear or auto power power format, depending on how I tell TestLab to calculate it. Make sense?
Yep.
Good. So, to add a little bit more intrigue here, we also have something called a PSD, which is really just a modified auto power. So when I started out, I just heard this term PSD. I didn't realize it was just a modified auto power. It's really an auto power PSD, or power spectral density. So what we're doing is we're taking that auto power spectrum and we're just dividing it by the frequency resolution, or the delta F. Okay. Averaging, obviously it's an auto power in its root, so there's no problem averaging. But now we'll get an even weirder unit, Pete, where we have Pascals squared per hertz or G's squared per hertz. Okay.
I think you're making my brain hurt.
Yeah. But you'll see why we would want to deal with such an odd unit in just a minute. Okay. And these guys are used all over the place to characterize the energy content in a stationary random signal. And when I hear stationary random signal, I think shaker table testing. Okay. I've got a landing gear on an airplane, or I've got, a radar antenna or something, and I need to know what kind of vibration profile it's going to see on this helicopter. And so I test it in a lab on a shaker table. I want to ensure that the spectral content, the energy content of that vibration signal is correct in terms of frequency distribution, but also amplitude, and that is what makes the PSD perfect for this type of test. Okay, and we will take another look at that. So adding onto our little chart here, we now have a PSD format of our auto power. PSD can be shown in peak, peak to peak, or RMS, and this is how the amplitude ends up being calculated. Okay, so it's just getting more and more complex, but there are benefits to this complexity. Lastly, just real briefly, there is something called an energy spectral density. All we're doing here is we're taking our AutoPower PSD and now we're multiplying it by the amount of time, that capital T, that we use to calculate the FFT. Okay, and that's the reason we would do this is because we're interested in an energy unit. Okay, so when I look at the energy meter on the back of my house, it tells me how many kilowatt hours of energy I have used, right? It's so many kilowatts of power over so much time. Kilowatt hours is an energy unit. Same exact principle here. So we have an energy divided by hertz, or a Pascal squared times a seconds per hertz. Okay, and we'll take a look at one of these. They're not as scary as the unit might lead you to believe. But same with PSD, we have a peak, peak to peak, and RMS, and now we've got yet another term in the unit amplitude here, okay? So if I plotted a spectrum in all of these different formats, you see I've got an AutoPower linear here, an AutoPower power, an AutoPower PSD, and an AutoPower ESD. If you look
Are they all the same there?
Yeah.
Oh, the same shape, but...
Yeah. So if you look at the shape of the curve, they're all identical. What is changing is the unit over here on the y-axis and the value here, okay? And so you see I've got a cursor at 10.5 hertz here, and I'm showing you the value in each of these cases. So the AutoPower linear is 0.38426, right? If I want to go from an AutoPower linear to an AutoPower power, what do I need to do, Pete? This is Pascal's, this is Pascal's squared. No, I'm going from Pascal.
From linear to power, square it.
That's right. So I square 0.38426 and I get 14,765. Boom. That's the amplitude of the AutoPower power spectrum. Now, if I want to go to PSD, do you remember what I do to get a PSD?
You take the squared number and divide it by the delta F, or the hertz, right?
That's right. So in this case, my delta F is a half a hertz, right? And so that I divide this value by half, and I get this 0.29531. Boom. That's my
I think I'll always use 1 hertz resolution. Then I don't have to worry about this.
Then these would be identical. That's exactly right. Now to get to AutoPower ESD, I would then multiply by my T. For half hertz resolution, it is fixed to be 2 seconds. And so 0.29531 times 2 is 59061. Okay?
Okay.
So all of these are showing you the amplitude versus frequency in exactly the same way. It's really up to you. What do I want this unit to be? And how do I want to share that with my colleagues? Okay? So why would I choose Spectrum versus AutoPower or a PSD? Okay? Let's take these two at a time. Spectrum versus AutoPower. Why would I choose Spectrum or AutoPower, Pete?
I know Spectrum has phase and AutoPower does not, but AutoPower has those screwy units.
That's right. Okay, so spectrum, I need to choose that if phase is important to me, right? I'm doing a phase reference spectrum or an ODS or something. I definitely need to use a spectrum. If I want to average carefree and just know I'm not going to end up with 0, I choose an AutoPower. Okay. Now, how about AutoPower versus AutoPower PSD, Pete? Why would I choose one or the other?
Because you like even more confusing units, dividing something by hertz.
Right. I need my colleagues to think I'm really smart, so I'm going to work with the most complicated unit. So I'm going to have this divide by hertz thing, right? Well,
I thought you said something like it's good for random data, but I wasn't quite sure what that meant.
Yes, that's exactly right. So in order to explain this, why I might choose one or the other, we're going to go through a little example. And the big difference here, you see I'm comparing an AutoPower on the left of this chart versus an AutoPower PSD on the right of this chart. And then the top row here is for random signals. The bottom is for periodic or sinusoid-based signals. Okay, and you see we get different answers depending on which format we choose for these two cases. In the happenstance or in the event that our frequency resolution might change from one test to another. Okay, so when I'm changing the frequency resolution between tests, I get these results as shown in this table. And we're going to walk through these one at a time to help explain it. Okay?
Okay.
So first we're going to look at a random signal and an AutoPower. So either AutoPower power or linear, but the levels come out as different. So come with me, if you will, to the local bowling alley, and we have two tables, okay, table A and table B. And each table decides they're going to go up to the snack bar and they're going to get a pitcher of, in this case, it looks like grape Kool-Aid. But they each are going to get a pitcher, and these pitchers are identical, okay? However, at table A, there are 4 people, and at table B, there are 8 people, okay? And they each have the same pitcher to share. So which table will be happier?
What's in the grape Kool-Aid? No.
Bunch of sugar.
If you
color.
if you like grape Kool-Aid, table A will be happier because each person will get more.
That's right. We're going to take that pitcher of energy and we're going to divide it among 4 people versus 8 people, right? And so table A is going to be happier because they all paid money for this pitcher of Kool-Aid, and they're going to get more than their table B counterparts. So the pitcher contents get spread over the number of glasses regardless of how many glasses there are, right? So if there are 4 glasses available, we're going to split it up 4 ways. If there are 8 glasses available, we split it up 8 ways. And in the case of 8 glasses, each glass has to get less energy, or in this case, less Purple Sorcerer X Kool-Aid.
It's kind of like a random signal. It gets distributed sort of evenly over
all of them. Yep, that's exactly right. So a random signal distributes that energy over all available spectral lines. Okay, so the more frequency lines, or the finer resolution, you will get a lower amplitude. Okay, so I've got an 8 hertz random signal in all of these cases, and I've got a delta F of 1 hertz, delta F of 2 hertz, and a delta F of 4 hertz. The pitcher is going to get spread across all the glasses in each case. If I have a coarser frequency resolution, 4 hertz resolution, it looks like I have more amplitude when I really don't. All of the pitchers started out the same.
And in this world of spectrums, there's no like leaking like in the 4 hertz case. You don't pour out in between the glasses. Everything gets captured in these glasses.
That's 100% right.
No grape Kool-Aid is wasted.
That's right.
Okay.
Okay, so that we get these levels are different with a random signal using an auto power. We're going to take a look now if we did a PSD in these cases instead. So remember, the PSD takes the auto power and it divides it by the frequency resolution, right? That's what the PSD is. And so in each of these cases, we're going to divide by the amplitudes by 1. Here, we're going to divide the amplitudes by 2. So these will get cut in half.
Because they're 2 hertz apart.
Yep. Here, the delta F is 4, so we divide each of these amplitudes by 4, and boom, we end up with identical amplitudes, regardless of a change in frequency resolution with the PSD. Okay.
Maybe so I don't have to measure only with the 1 hertz delta F if I use PSD.
That's right. With a random signal. That is 100% right. Okay. Let's see how things change, though, if we move to a periodic signal. How is a periodic signal different? Well,
this would be like almost like a sinusoid, like at a discrete frequency or something.
Yeah, indeed.
Okay.
Like 4 hertz. Instead of being all frequencies in this pitcher, we just have 4 hertz in this pitcher. We have a single sine wave in each. And so in this case, we don't care if there's a number of different glasses available, because the periodic sine wave, 4 hertz, is only going to be going to the 4 hertz spectral line in each of these cases. Right? There's only one frequency here, so it only uses one of the glasses, and so they all end up identical.
So whoever's at the party with the 4 hertz cup, they're happy, and everyone else is sad.
Yeah, exactly. For a sinusoidal signal, that's right. Now, PSD is going to come along and screw this up for us, though, because, again, we're going to divide by the spectral resolution. So this 1 hertz delta F guy, he gets divided by 1. He gets to keep all his Kool-Aid. Delta F equals 2. We're going to divide this amplitude by 2. Okay, so we've just introduced an error. And then this delta F of 4 hertz, we're going to divide by 4, and we're going to introduce an amplitude error. Okay, so PSDs can screw up your amplitude if you have mostly a sinusoidal signal. Okay.
So like if I have something that's just generating discrete tones, I'm probably better off not with the PSD. But if I have something that creates broadband random, then I want the PSD. That's
right. And in the real world, you really likely have a combination of both of those, right? And so I'm going to show you those scenarios. So you see I've got a mix here of broadband noise shown by this sort of, flat lines in the frequency domain, but then I've got these big frequency components that stick up. So I've mixed tones and background noise. And in this case, I'm doing auto powers, and over here I'm going to look at the same signals but calculated with a PSD. I'm going to zoom in here on this peak, and you see all of the broadband amplitudes. If I go off the peak, these are all quite different by 5 or 6 dB, depending on which frequency line I'm at. But you see 3 different values, right? But if I go right to this peak, boom, now the peaks are a lot closer together in terms of amplitude. So if I go to the global maximum, you see, boom, right at the peak, they are less than 0.1 dB different in terms of amplitude, okay?
And so this is a regular auto power, not the PSD.
That's correct. This is an auto power, so it's screwing up the amplitude of the broadband part of the signal, but getting the tonal or the sinusoidal part perfectly right.
I see.
Now, if I go to do a PSD to fix these broadband signal parts, let's zoom in again. So now we see the broadband random portions of our signal are all lying on top of each other. But now what have I done to my sinusoidal component? I've screwed it up by dividing by the delta F. And now my peak amplitudes and my sine wave components are now introduced that's 6 dB different.
So
Okay.
it's Pascal squared per hertz. The random is very similar because you're
Yep.
PSD, but the sinusoid's all screwed up. Got it.
Got it. So now let's look at our good friend, the vacuums, right? We use these vacuum recordings all the time where it looks like we have some sinusoid part of the signal mixed with some broadband. However, in a real world signal, it looked like a tone, when we were zoomed way out, but when I zoom in on this guy, that spectral line, that tone that vacuum makes moves around enough that my auto power is still going to have a significant amplitude difference on these tonal like components, and I'm better off, even with a real world signal, using the PSD, because you see this isn't really a true sinusoid. It's moving around enough in real life to spread that energy out, and the PSD captures the amplitude much more accurately. Okay.
And go back to the auto powers where they looked very different. I was kind of curious. I know you can do this double X cursor and calculate an RMS.
Yeah, I sure can.
And if you, yeah. And maybe do a pen cursor position and turn off the, a pen cursor position. Okay, so this, even though visually they look different, the signal, the energy in the signal is the same, huh?
Yeah, the energy is still there. It just doesn't get distributed all to one frequency. It's spread across all of the spectral lines. And so by summing them all up, I get that energy back.
Good trick is to do that double X cursor with a sum. Okay, thanks.
Yeah. Even when you take on part of the presentation, Pete still ends up doing the presentation. Leakage in windows. So what does leakage mean? Well, we'll define it as when the spectral content of your signal does not correspond to a spectral line that you have available in your analysis. Okay, so let's go back to Pete's 1 Hertz delta F, right? He's got 1 Hertz delta F. He thinks this is going to get him out of all his problems. Well, bad news is he's going to be trying to measure a couple different signals. The first one's going to come out pretty easily. He's got a 5-volt sine wave at 3 Hertz. He's got a spectral line right at 3 Hertz, and so this is going to be his frequency spectrum, right? Typically, we like to connect these answers with straight lines, and so we would get 5 volts right at 3 Hertz, and this would be perfect, right? No leakage here. What if I then told Pete with his 1 Hertz delta F to go measure a 2.5 Hertz sine wave? What is he going to do? Well, we don't have a spectral line at 2.5 Hertz, right?
Yeah, we don't, so it just disappears, right?
No, it's going to get nicely evenly divided between the 2 and the 3, right? And so we're always going to know that it was exactly 2.5 because these are exactly half, right?
Wouldn't that be like 2.5 at 2 and 3? It's not quite right.
Yeah. ultimately it's not what happens. When we have this leakage, we don't just get a nice, easily solved problem. What we end up with is spectral energy leaking across all spectral lines of our frequency spectrum, and we cannot figure out what the frequency content was. Okay, so we need to avoid leakage at all costs.
It doesn't disappear, and it doesn't just go into the adjacent spectral lines. It goes everywhere across the frequency range. That's
right.
wild.
Yep. Let's say why this is. Okay, so the spectral energy leaks across all spectral lines. That's why we call it leakage. And so what does this look like in the real world? Well, the red trace here is a perfectly sampled and performed frequency spectrum. You see a nice round 1.0 amplitude. This blue trace is where we sampled the same data, but not in a periodic manner, and so we get this leakage across all frequency lines and a reduction in the amplitude. Okay, so this is the effect of leakage in a real signal. So why does this happen? Well, if we've got a periodic signal, right, this signal sine wave repeats over and over, and if we do this exactly right, and we measure our capital T observation time, right at the peak of the sine wave, right to the next peak in the sine wave, and we push stop real accurately, we end up with this as our sample for this continuous sample or signal, right? I then take that and reconstruct the original signal using that sample, and I end up with this. So I'll ask you, Pete, is the bottom signal the same as the original signal?
At least over the area where you repeated it, it looks the same. I guess if it kept sending that out, it would keep looking the same, yeah.
Yeah, my sample is an accurate piece of the full signal when I reproduce it. Now, in an aperiodic sampling scenario, I push stop a little bit too late. I was trying to hit this peak value right here, and I didn't get it, and I don't stop my measurement until this point now. So now this is my sample, and I take these samples and I line them up end to end, and I recreate an additional from my original signal, and this is what I would get, right? So are these two signals the same between top and bottom?
These, I can say, definitely aren't.
Right. We get this huge discontinuity here, right? Where it jumps very, very quickly from this low amplitude up to the top. And we talked about these sharp edges in the time domain end up being very broad, or tons of frequency content in the frequency domain. And so what we'll end up with is this leakage across all these frequency lines. Okay. So what do we do to try to mitigate these effects? Well, we're going to multiply by something called a window. Okay, so even if we sampled aperiodically, we go with our worst case scenario. If I do a multiplication by this thing called a window, that is a function that starts at 0, ends at 0, and goes up to a value of 1. If I multiply the blue times the purple window, I'll end up with this windowed signal. And if I take that windowed signal and recreate my original signal from that, it's at least continuous, right? I don't have any of those sharp discontinuities in my signal anymore. And so I'm going to minimize the amount of leakage that I have, right? I don't have any sharp edges in this trace, right, Pete?
Yeah, there's no sharp edges, but it doesn't quite look like the original, but it's somewhat usable. What ends up happening here?
Yeah. So the window forces our signal to be periodic by making it 0 at the beginning and the end. We don't have this impulse or this sharp edge in our signal, but as we're going to see, we have a reduced energy and a reduced amplitude in our windowed signal. Okay, so we're going to apply these windows, and they're going to each have a different sort of application for us, but they're all there to help us minimize leakage. Okay, this guy called a Hanning window, it's kind of the one we used in our example. Nice bell-shaped curve, sort of a sort of generic purpose window. There's also one called a flat top, which is really good at maintaining amplitude accuracy, and so it's often used for calibration. Then there's something called a uniform window, which is essentially a value of 1 for the whole observation time. So you're applying a uniform window if you don't apply a window, right? The effect is exactly the same. And so you'd apply a uniform window when you know your signal is going to be 0 at the beginning and 0 at the end. Again, in an impact testing sort of scenario. Okay. Some other types of windows you can use. Force window, again, impact testing where we have an impact hammer. We are really interested in this impulsive part of our force, maybe setting down the hammer. We don't want to have any of this little noise on there, and so a force window is essentially 1 during the impulse event and then off for the rest of it, and we end up with this nice clean impact event and then no signal noise. It's going to help us get a nice leakage-free impact signal, and it's often paired with an exponential window, which we'll use to force a signal that's still oscillating by the time we come to our end of our observation window. We're just going to sort of artificially damp that vibration out so it's 0 at the beginning and 0 by the end. Okay, and this exponential decay artificially adds some damping, but we know what we're applying. We can back that out after the fact. Okay. Now these windows all have side effects. There will be some frequency smearing. There will be some amplitude loss, as we saw. And so this Hanning window is sort of a nice balance between noise smearing, frequency smearing and amplitude error. Whereas this flat top window we talked about, it has pretty bad frequency smearing. So this flat top is shown here, but its amplitude error is very, very, very small. Okay, so we use a flat top for things like calibration, where we know the frequency is going to be what we're sending it through our calibrator, and we want to make sure our amplitude is very, very accurate, and so we sacrifice frequency smearing for amplitude. Okay. But as Pete said, this is our original signal. We're going to window it, and this is our windowed signal. This guy in red does not look like the original signal, right? It's reduced in amplitude and energy distribution between the top and the bottom, and so we have to account for this. The nice thing about these effects for a given window is that we can account for them in a display. Okay, so our perfectly sampled sine wave is shown in blue here. I use a Hanning window to create the red spectrum, and we see the amplitude is definitely reduced. The energy is distorted as well, but we don't have as much leakage as we would if we had not used a window at all. So we have a lower amplitude and our energy content's distorted a little bit. The nice thing about these windows is the amplitude correction and the energy correction are known values. Because we knew what the window functions were going in, we can calculate the effects on amplitude and energy, and so we can counteract that. Okay, so for our Hanning window example, we see our amplitude correction is 2, so you see our amplitude is exactly half. So if I want to correct for that, I just multiply my amplitude by 2, and boom, I've got my amplitude perfectly corrected. You'll notice my energy is still not quite exactly right. It should be looking like the blue. So now let's do an energy correction. Energy correction is 1.63, and so we can correct for the energy as well. So here the energy, or the area under the blue curve, is identical to the area under the red curve. You see I had to bring this amplitude down a little bit in order to correct that amplitude energy error. The only bad thing about window corrections is that they cannot be both applied at the same time. We can correct either the amplitude or the energy, and it's really left up to us as an engineer or the tester to make this decision and apply one of these corrections. Okay? So to sum up everything we talked about today, we kind of took a mad dash through DSP, but we started out with the Fourier transform. It's how we break up a time domain signal into its frequency spectrum components. We talked about the different formats these spectrums can take. They're all, remember, complex numbers. And to start out with anyway, talked about some of the considerations we need to make when we're doing the sampling, when we're actually digitizing this analog signal. Then we have to tell our software what kind of spectrum do we want to calculate if we do a spectrum versus autopower versus PSD. Remember, we have some considerations there. Talked about leakage and what can happen if we have an aperiodic sampled signal and why we use windows to try to minimize that leakage. And then we talked about when we apply those windows, some of the things we can do to correct or back out those errors we've induced by minimizing our leakage. Okay? Thank you for your attention. Anything you'd like to say in closing, Pete?
Scott, that too was an amazing journey. I thought the measurement chain was amazing, but that's amazing as well.
No red blood cells attacked us, but still pretty exciting, I think. So
Yeah. Thank you.
awesome. Thank you.